Yeah. I was. Alright, that's it. That's it. So, what did we do last stream? So let's find out. So all over again. Did I even? Oh, basic lower the LIR. Okay, I need to change the name of this. How do you do it? Is it get re something? Let's get something. How do you change the name of a commit? Rebase. Hold on, we'll talk about that soon. You copy the. Yeah, I do this while I wait for people to come. How do you do it? Pick? Reword. Okay. Is that the right one? Uh-oh. You know what, forget it. I'm not gonna rename the commit, but I'll put a note down to rename it. Hold on. Okay. So, what we did last time is essentially this. LIR, basic lower to LIR. So this is just doing lowering. So how it worked is, we created this file called lower.c, and I'll open it right now. That essentially just ran over all the symbols and created turned them into LIR. And LIR is essentially a trimmed down version of HIR with assignments, control flow, returns. They're all delegated to statements, and they're not expressions anymore. So, if you go here, lower proc, it constructs a value and then creates a new statement returning that value. It's simple, super simple. And here you're just returning expr array. You're just calling this and returning. And assignments are statements as well, and just you're returning of L value of reloading, things like that. Not very important, but I'll explain what it does. Don't read what I have here. I'll read it to you after. So let's take a look at something like this. F equals ret 20, right? So essentially, you're gonna end up doing like a double ret, because this ret expression it returns no return, which is not right. So what you'd want to do is you'd firstly want to recurse into F, and you'll hit a ret expression. So let's just say these are the list of statements that we have, right? So we construct a list of statements for a proc, and we pass those in to here, desc lir.statements. So we hit a red instruction. Okay, emit a red instruction to here, and then return poisons, something like poison. And then essentially what this thing compiles down to is f equals do ret 20. So this is this kind of like statementizing sort of thing. You're like so this poison is just some implementation detail, but we're essentially statementizing this whole thing. So let's say if we wanted to do like c cond bool, oh yeah, just c and then f equals if c 20 50 else 12. Okay, so how could we statementize this? So this notion of statementizing, making things into statements, making these into an imperative language. So this is essentially what lowering is doing. We have a couple of these things. We have a couple statements, and we're turning them. We're matching on expressions and turning them to statements. So for assignment, you get the LHS, RHS, and then you construct a statement assign. But a statement assignment isn't an expression. It's actually an assignment is an expression, but what we just did is we constructed the statement, which means we're going to have to return a new value of constructing right here. We'll have to construct an L value to reload that local. This is exactly how I implemented the original parser, right? The parser for LIR, which was just like a control flow graph sort of thing. So how can we statementize this? So this takes in a bool right here, and then we can statementize it by just constructing a do, and then going we can do if c do, then we have some more statements, and perform an assignment here equals 250 else, and now remove the do's. Just assume these are statements, and then the else can go 0 to 12, and then you can perform the ret 0. So what we just did now is we basically statementized. So if the if cases, these aren't expressions anymore, they're assignments of variables. So that's another example. So here's another example. We can do something like let's do something like if f c bool v value is a mutable i32 equals if what could I do? Like if v equals 50 greater than 50. Yeah, just ignore what I'm doing this for. V else 50. Okay, let's go ahead and lower this. This is completely nonsensical code. No one's gonna write this, but let's just lower it. So we could lower it by starting to turn these into statements. So we can create a do block, and now we can put all these statements down. Now we're going to recurse into the condition of the if, and then we're matching on here. V equals 50. This is an assignment. So what we would do is we'd just write it down as is, and then return a reload of 50. So we write down this as is as our first statement. This doesn't evaluate to an expression. It's just a statement. And when we're computing this this thing, the greater than 50, it would do that. So we're essentially turning this whole expression here, we're extracting this out to a statement, and then we're using that return value, this reload of the v, in another expression. Now we can continue going like this. Else v, so we could 0 equals v, else 0 equals 50, and then we can just go ret 0. So there we are. We just statementize this thing by reducing the if to have a intermediary value, so this underscore 0, and the v, the assignment to v, is essentially unpacked into a statement, and then the v is just being returned here. So this is this really easy like normalization. I want to bake in this notion of normalization. So what the LIR basically is a list of statements and a list of expressions. What we've basically done is we've made this this notion of normalization already. So if we're just creating a list of statements, why can't we do that inside the HIR? So this is like this thing I want to do. I want to not use the LIR yet. I want to see how far I could get by performing a normalization pass on the HIR without going overhead, using this overhead and going in deep on another IR, the LIR, which essentially the LIR is just a trimmed down representation of the HIR. So why can't we just use the HIR? That's my goal here. This normalization pass, or statementizing, imperative language conversion. So that's what I plan to do this stream. So I have at the top here. Why not LIR? Existing LIR is just lowering HIR into statement HIR. So the statementizing. The only optimizations we perform is conditional constant propagation in DCE. We're gonna do this on an AST anyway. Via vscode. Oh, okay, fine. It's Sweet Dracula Monakai. Good. Done. Yeah, okay, so the only optimizations we perform is conditional constant propagation in DCE. We're gonna do this on the AST anyways, because the LIR is a tree representation anyway, right? So we're essentially just shooting ourselves in the foot by constructing a whole new LIR, when in reality the LIR has all of the characteristics of a HIR, but we've just moved all the statements separately. So all we have to do is construct HIR and normalize it. So, normalized. All control flow expressions that return no return would be lowered to explicit statements. This is with this if statements or explicit statements, and especially the return. So if you have a function like this, f equals 20 plus ret 50. So what's going to happen is, obviously we're going to have to lower this to this, ret 50, because we'd construct the 20, and since the left-hand side is a no return, we can just ignore the other half. But what if we had something like this, which had a side effect? If let v equals 50, ret v, so v is 32. What if we had something like this, where the left-hand side performs an effect, but the right-hand side is a no return? So we're going to have to propagate this value, but we have to return. So we can start lowering it just like this. We go f, like this, and we'll recurse into the left-hand side. Going into the left-hand side, we'll construct a v equals 50, and then return the v. And then we'll return the v, and essentially we'll go into the right-hand side now. We'll construct the ret v, and then return a no return. So this is a poison, essentially. So right now we have these two things. It's essentially v plus no return. And what happens is, to construct a no return, there has to be an effect before here. So it'll already have the return as a statement. And then when we get to here, we can just delete this. So this is what lowering essentially does. This lowering, not lowering, we'll get this lowering anyway from the LIR, but normalization does the exact same thing. So we'll get this normalized to this. This is what we'll end up on. Yeah, so function value expressions is now a ret inside a do expr. Yep, so we'll need to construct a list of statements. There is always an explicit return at the very end. All no return code has been DCE'd. Like I explained, you're essentially going to DCE the left-hand side. It's going to be gone. Here, proper reassociation. That's a separate thing. I want to do it this stream because I feel like it's one of the simpler things and it will be a good learning moment. Show you guys. And here, all assignments are statements. That's essentially what we're going to do anyway. All assignments are statements. So I already worked on a little bit of this thing. So instead of lower, it'll just be called normalize, or normalize expr. I'm just going to call it normalize. And essentially, what we have is very similar to what we had before. And I'll bring them up on both sides. So we'll go to L proc. And here we can go to N proc. So lower proc and normalize proc. So essentially, in nproc, we construct a list of statements. Well, a list of statements, but they're basically expressions. And then we just do a mem copy malloc of the original expression here. This is the top statement. Okay, and then we construct the return value. We call NHIR expr, so normalized HIR expression. Pass in the desc the list of statements, like we have here. We're passing a list of statements, and the expression. So we're calling proc desc HIR, and then we're calling this on the duplicated version of that. NHIR expression mutates the expr, so it mutates it. It's edit in place. All right, and then does not equal st poison. I'll explain this this st poison thing later on, right after. So if we construct the NHIR expression and we edit it in place, we construct a return with return d-return expr equals HIR, and then we perform our push. So we push a new statement into the returns. And then what we do then is we construct a new proc desc HIR, so this is the new expression. And it's just an expr do block with list of statements. So that's essentially what we're doing. It's essentially a carbon copy one-to-one, except for this poison thing. Okay, so I'll explain this this poison thing and how it works. It's just like before with this with the here the deletion of the left-hand side operator. So we're gonna call essentially n infix. We're lowering the infix-ness. Let me go. Yeah, so we're lowering the left-hand side and the right-hand side. So we're gonna pass the left-hand side. We're gonna go LHS 20. Okay, that just gives us 20 back. Nothing happens. So let's just write st none. Okay, then we'll do the right-hand side. It's a RHS ret. It's a ret, so that this returns a no return value. So if your recursing thing sees it, this will return a st poison. This poison? Yeah, poison. Yeah, so this returns an st poison. So, and then in c infix, n infix, essentially, if yeah, so I'll just look at the code here. So, yeah, so expr infix. So transform LHS and RHS, and then so we're transforming them, and then we're checking for poison. And essentially, what this expands to, does that work? Yeah, it expands to yeah, it expands to poison expr. So if expr equals st poison, return immediately. So if the left hand side gave a poison, return. If the right-hand side gave a poison, immediately return. So we're essentially like performing DCE by just ignoring expressions and just leaving them to leak memory. Yeah, so this is st poison. That means just return, do nothing. And what will this and returning an st poison within the evaluation of the RHS of ret, it would have already stored a ret 50. And then the return is st poison, and we're essentially ignoring the left and the right hand side. It's like this like short circuiting sort of thing. It'll eventually get more clearer as I implement it. I have to manually change the exposure time. Does that work? Hold on. Okay, well that's brighter. That's brighter. That should be easier. So I've essentially done basically nothing so far. Integer lit, bool literal, tuple unit. These do nothing. Expr infix, you're just transforming the left and right, checking for poison and doing nothing. Well, we don't actually return poison in any case, but yeah, it's right now we're just not doing much. So I can show you what happens when we perform the normalization pass. And how the passes work is we go to pass.c. So I've essentially hoisted out all the code from the checker. Compiler pass all. You pass reorder sanity, returns a list of post orders, and then check all, normalize all. Normalize all is in this function. So right here, normalize. Yeah, normalize. All right, check main.t and normalize. So we have main.t returns infer HIR equals 2. We perform checking, normalizing, and then the return is essentially what happens is main.t i32 HIR equals do ret2. Simple. Yeah, it's well, it's simple. It's really simple compared to like constructing a new an LIR and everything. So what I want to get done this stream is essentially lowering. Let's start lowering returns. Let's get our example. This one, f equals 20 plus ret 50. It'll invalid operation plus on non-numeric type bang. Okay. Let's do this, or type. Yeah, we'll have to do this weird kind of unification. This is annoying. Or type. Just type. Yeah, this is annoying. Invalid operation plus. Oh yeah, I'm gonna put that in this thing. Wait, why is that still erroring? On non-numeric type. What type equals type bottom? Where's that coming from? Okay, if type is number, or type is bottom, and it's not that. I don't know where the error is coming from. Non-numeric type. Oh, wait. I'm stupid. Fuck. RHSD. Okay, good. Okay, we'll run it. So it performs assertion 0 unreachable. This is obviously the return, so expr return. And we'll start normalizing that. So we can just go like this. So n, we'll do poison. So we're gonna check, we'll do poison, and then d-return expr. So essentially what we're gonna have to create is a new statement. So we can do this. Expr return red. So the d-return. Oh, we can just repush the existing return and then go return st poison or st no return. I don't know. St poison's fine. Okay, well, all we have to do is just push stimulus expr, right? Yeah, that's right. Push statements expr and then return st poison. So I think it's fine. Does that work? We just did it. Look at that. Ret 50. 20 plus ret 50 just goes to ret 50. So we've essentially no returned the whole thing. That was easy. That was an easy operation. And the reason why it works is the expr return is going to have to go to a statement. So we can just repush this into the statements. So we check for poison on this like d-return thing. And then, what? Thanks, Jamie. Thanks for the chat. Thanks for showing up. Okay. Expr return. Anyway, NHR expr desk statements expr d-return expr, and then we just call it with poison. So if a poison never returns, we just unwrap the call stack and just go immediately straight down. Yeah, so R push statement expression then return st poison, and in here an expr infix. So what we'll get back here in a.rec. So we'll get 20 back, right? And then we'll get poison. So we'll get poison back. When that happens, just immediately leave and ignore the value. So this goes all the way down to here. If NHR expr is not equal st poison, all right, hold on. Yeah. So constructs a return value only if NHR expr is not an st poison. So we went all the way down and we propagated the poison to here, which means we can basically ignore this whole expression because the return will already have been done. And that's what we can do it. Easy. It's just a ret 50. And we can even do this. Ret 50. Like that. And it still goes all the way down to a ret 50. There's no need for this, all of these things get unwrapped completely. 255, we're going to do like ret 5 plus ret 255. And you can see, it only goes down to, is that ret 255? I don't know, is that, I don't think that's supposed to happen. I think it's supposed to be ret 5. Which order do we do them? LHS and RHS. I don't know. I think it's supposed to go... yeah, because you're recursing all the way down to the right. I don't know. I'll comment this. No, I'll leave that for later. Anyway, we did that. That's basically the first thing. All control flow expression. So let's do the next example, which is this one. F v mutable equals v equals 50 plus ret v, and then we'll see what happens. Right now it's an error because we haven't done call. We haven't done call assign. So where is that? This thing expr assign. Okay, well let's bring this up to the top. So our push statements expr. Wait, that's easy. That's actually the easiest thing in the world because expression is already a statement. Wow. This lowering is super easy. I'm pretty sure that's it, right? Wait, no, not poison. No, it's st. Just break. There's no poison. Alright, where's the error coming from? Plus ret v. Okay. We're gonna do expr local. Okay, when you do that. Which, do nothing, because you're just reading from a local. Yeah, do nothing. Yeah, I'll have to make a note. Because you can store no return inside a local. Yeah, do nothing for locals. Good, so v equals 50, ret v. That's it. That's literally what we just did. So we basically statementized the whole thing. Yeah, I'll do a clear. As always say at the top. Yeah, so v equals 50 plus ret v. So that's it. That's the easiest thing in the world. Oh, I didn't know. I didn't expect that to be that easy. Okay, so function value. Yep, all that's been DCE'd. That's good. Reassociation. All assignments are statements. Okay, well let's do ifs. Now. All right, let's ignore that. Okay, let's do ifs. Let's do this one. It's f c equals bool if c 250 else 12. So we'll run it and we'll get an error. Okay. Well, what we'll need to do is insert intermediary assignments. So let's do this one, expr if. So perform poison on cons, because the condition can poison itself. And then we need to construct a intermediary expression. So we'll do assignments. Intermediary local. So we'll go IR new IR local new. Go desk, the scripter, and we'll just construct a new local. And we'll make its name. I don't know what you want to name it. I think I'm just gonna ISTER none. But it has to be something, otherwise my printing code's gonna choke up. Okay, kind is local im, because it can only be assigned once. And what's the type? I don't know what the type's supposed to be. Ah, it's just the type of the expr.def, right? Expr.type. Yeah, and then the lock. What's the lock supposed to be? Yeah, expr.lock. And I think that's type lock as well. It doesn't have that. Okay, ISTER none. So we're gonna have to make that make it a proper name. TMP name. Okay, so we have a local, so it's just our local team. Local. All right, and then we can replace the expr dif with a list of new statements. So we need to construct a new block. We should create a function for that though. Okay, so we need a LIR, HIR expr then, which is just a expr which is an expr do block. So it's a list of statements, and we need a. Yeah, we'll get it. We'll put statements into something separate. We'll go HIR expr then statements null. And then we'll start doing this. We'll put that here. And this here. Then an else here, and then we get the value of that. We'll have to watch out for poisons, because I don't want it to. I want to still construct the if. We'll need to do poison for the top though. So we can do this. If MHR expr equals poison, it's not equal st poison. We can generate the generate assignments, and then just duplicate it for this side. Right. Okay. We'll create a HIR expr assign, and then we'll the LHS will just be a dump new expression with a local. Just kind for local d local equals local, and then we'll put its type as the local's type. And the RHS is this, right? Yeah, I mean, that seems right. That seems right. Okay, and then we'll just duplicate it for this side. So, enter. Great. And then we can just construct a new if. So we're going to have to edit the if in place. So actually, no, we cannot we cannot edit the if in place. What we have to do though is we'll have to return a new thing. So let's create it. Let's create an if as a statement. We'll not do it in place. If statement. Okay. That seems about right. Type if bottom cond equals the expr if cond, because we have that. We'll have to wrap this in dup though. Wrap this in dup. What's the error? Why is that happening? What else? Why is that not working? Ah. Yeah. Still not working. Why not? Hey, try your dub. No. Okay, well, I don't know why that was giving me an error. Thanks, Clang. Great. Do block type bottom, else statements, then statements. Great. I think that's good. And then just repush. So we'll repush this with that. And then what we can do now is this whole expr is gonna be rematerialized into something else. Expr local, expr type, dlocal equals local. Simple. We'll create the lock. We need to redo the lock to its right place though. Lock is expr.lock. We didn't give this a lock as well, right? Lock. Yeah, we'll just please. It has to be expr d else lock and d then. Okay, well, let's see. I think that worked. Yeah, it seems about right. I mean, if C, create a do block, and these things like they're not on the right line, which is just fucking stupid. And then equals 250 else create a new do block underscore 1 equals 12 ret 1. I wonder where the underscore 1's coming from. I think no, I think I already have code for that. Okay, good. Well, that's the second thing we just got done. It's a ret underscore 1. Great. Done. Easy. What's the next thing? We'll do a loop. Yeah, let's do loops. I feel like we could get C code generation by the end of this. I feel like that'd be easy. I feel like we could just do that. Let's see. Let's see how we go, because we're only at 40 minutes in. Usually I have a lot less done by then. Okay, well, now we've got that. Let's bring in a larger function. Let's bring in something larger like factac0. Alright, let's bring in something like this. So, now I'm gonna write proper things on where it fails. Kind. Let's find out. Okay, kind 21. What is that? What's 21? Expert cool. Alright, easy. Well, let's do it. Cool is one of the easiest things to do. It's just I think you can fill it in for me. Yeah. transform args, expr decall. We'll have to poison the thing. HIR expr estimates and the expr decall f. Yeah, we'll do the f. All right, and then we'll take the address of that. Easy. Well, what else? Kind 19. It's 19. Symbol? Expr sim. Okay, well, symbol is just you do nothing. Yeah, do nothing there. Yeah, what did it generate? It generated if less than or equal to n1. It goes to do underscore 2 equals ac, else do block, underscore 2 equals fact ac, equaling it with negative n1. The second is n ac. Ret underscore 2. Great, easy. I'll bring in the next one. But I feel like this should be easy as well. Yeah, simple. What else? Let's try and support everything. So we'll go one by one and try and support everything. Arrays simple, tuples are simple, lambdas no. Do block. Let's do do block. Because do blocks they're special in a way that there's labels and stuff. So start here and we'll go do. Okay, we'll create a main function. Main equals do 50, 60, 23. Alright, well, the error is on 7, and that's definitely the do block. So, how are we going to do it? First, we need to find out if this do block has control flow, is branchable. Which, is it branchable? That's the thing. Now, the way blocks work in this sort of thing, the way blocks work is as you enter blocks, the compiler has this internal counter. So let's say you're right here. So the current counter is, let's go block ID equals 0. Then when you get in here, block ID equals 1, block ID equals 2. And essentially you have this kind of internal data structure where if you're in here, you can go blocks, block ID, and then get information of your current do block right here. What I essentially want is, I don't know, there's this kind of persistent block data structure that stores the labels and things and what blocks have control flow and what doesn't. So blocks without control flow should have no block ID, essentially. I mean, here, I'll have to make an alteration to the block, so we'll just do main equals 50, and see here it's a :0. That means this thing has basically a block ID, and I don't want it to have a block ID. So what I want to do is I want to pass it block ID none, and we'll create that up here in the HIR. Let me do this. Define none, which is a U8 -1. Good, and then we can put that over there. Block ID equals block ID none. It's empty. Well, here it'd be 255, but we're going to check against that. Which we can do in the table. All right, let's check against it now. Okay, and then I'll just create a function for just print block ID. It's just a U8. If block ID equals block ID none, nothing. Yeah, we'll do this. Sure, and then where do we read block ID? Spaces here. You can just do that. Loop. BRK and ret, they have explicit block IDs, so they can't be empty. Alright, so now this do block has nothing in it. What we'll need to do now, though, is we'll need to transform the blocks into something. And the way we can do that is... I'll have to figure it out. We can start like this. We'll go to the checker. We'll call check expression. And I'll move this invariant stuff. Actually, I'll keep it there. I should have done this off stream. The block ID stuff. Or I could do it now. I don't know. I just wanna know that a do block has a value. Yeah, we'll check. If the easiest thing we can do right now is BRK. Yeah, we'll go inside parser expr is BRK. Okay, where do you store the block stuff? Here is BRK. So if broken to, which means is broken to or is ret to. See, we need to store if a block ever gets referenced. You know what would be easy? Okay, we'll forget that for now. Actually, we should probably remove expressions that use the null, like empty type. Well, I'll think about that later. But what's most important is the do block. So we'll just start doing codegen on it. You know what I'll do? I'll leave this for later. I'll leave this for later because this is pretty important. Something I should solve off stream. What I should do now though is reassociation. And I'll explain what reassociation is. Essentially, it's a pass. Reassociation. LLVM. LLVM reassociation pass. Essentially, what it does is it reassociates expressions in a way that makes it easier to work with. Let's go godbolt. Godbolt, and I can show you an example. I'll do it in Rust. This is a good example. So, we're in Rust now, and then we can do something like this. Static static something fd2 equals 255 plus, actually no, it has to be a function. Pub fn ret num is a u8. This whole thing returns a u8. Num plus 255. And this shouldn't produce an error to the compiler. No, it shouldn't. Okay. This shouldn't produce an error to the compiler. No, it shouldn't return an error. But what should is 1 plus num plus 255. This should error, right? Does it not error? Oh, wow. Why does it not error? Oh, let's do this. 155. Yeah, out of range. Fine. What? I swear I've gotten this error before. So it can be like signed. I8. Okay, well. Alright, where's the error from? Alright, forget it. I swear I've seen this error happen. Anyway, I'll explain what this error is. Let's do reassociation. So, take a look at this right now. Let's assume num is a U8. So, if you look at this, what's going to happen? Is an overflow going to happen? You could probably assume that it is going to happen. Because association is commutative. Additive. Commutative. What is it called? Commutative, associative, and distributive laws. Well, I want the Wikipedia. Commutative property. Okay, essentially, x times y equals y times x. X plus y equals y plus x. Yeah. Essentially, this is the commutative property. X multiplied by y equals y multiplied by x. And this holds for integers. With floats and things, I think they have commutativity. I don't think they have the distributive property. Something with IEEE floats, you can just ignore them. But for now, we're looking at integers. And integers, the commutative property holds. So x plus y equals y plus x. X plus x multiplied by y equals y multiplied by x. And if you look at this, what is the best way to rearrange this expression to get the most out of error handling? Right? You want to know that this creates an overflow. Even if num was 0, this would still be an overflow. 255 plus 1, when they're unsigned 8-bit integers, will overflow. So, we can do this. Num equals, num plus 1 plus 255. Now, these are right next to each other, and you can easily tell when something overflows. So, we're taking advantage of the commutative property to reassociate expression. So, we're going to reassociate 1 plus num plus 255 to num plus 1 plus 255. Simple. It's one of the simplest things. One of the simplest optimizations you can do, and it's not really an optimization in the sense. It's just for error handling. It's just better error handling in the language. It's just to catch simple overflows, right? Because you don't want someone doing overflows. And I wrote a note here. Case expr infix. So this is inside the infix expression handling. So perform reassociation, but not constant propagation / eval. So this is just for reassociation, or it'll make const prop easier, but reality that's not our goal. So const prop and eval. These are some optimizations for if constant evaluation, things like that. That is left to further passes where compile errors are raised. This is just to catch overflow errors easily. We'll have further reassociation passes in later IRs. Okay, so here, overflow errors don't make sense of floating point numbers, so ignore them. Yeah, so this is just reassociation and IEEE floats. IEEE floats. Okay, so essentially, expr infix goes like this. Transform left-hand side and right-hand side, you check for poison. And then these are the rules. T are terms, C are constants, constants are also terms, so they can fall back to terms. So, like we said, A plus C, 0, equals 0 plus a. This is our first rule. And then there's rule 2. A multiplied by 0, or constant, equals, goes to 20 multiplied by a. And then the next rule, a minus this thing goes to negative 50 plus a. And then the next thing is just moving. We're moving groups of expressions to the left, and these are moving groups of expressions from to the right to the left. And then once they're moved from the right to the left, we can check these constants, and then constant fold these things, moving constants this way. Essentially what we're doing is we're moving all the things we don't know about, our terms, to the right, and all the things we do know about, the constants, to the left. This is reassociation. It's one of the simplest optimizations. But we're not using it as an optimization. We're using it to check overflow. So let's do it. So essentially, we're gonna have to go one by one for each rule. I think we'll just go 1, 2, 3, 4, 5, 6, 7, all the way down. So first we'll have to check constant stuff. So let's go if expr dot, and then we'll extract these to left hand side and right hand side. So let's turn these into pointers. Okay, so also in places like this, you get a let v equals 0 plus 50, and let's say we'll do let k is a u8 50, and then 0 is u32. Okay, so essentially you can't have these integers or accessing locals without a cast. So the compiler would insert explicit cast. So let's say you had this thing, right? K would be explicitly cast to u8, which means it would stop matching on any of these terms. So this is just a nice safety guard where all integers and all terms added together will always be the same type. So the left-hand side and the right-hand side of an addition will always be the same type, or any kind of operation. So we can just assume if we don't match, if it's a cast, we can stop doing the reassociation test. So let's go if kind equals essentially we can match on anything. When I say term, I think it can be literally anything, like an if statement and things like that. But constants, though, we have to check if they're constants. So let's just go expr.kind. So we'll have to go rhs.kind equals expr. Oh, well, not integer literal. Do we have any other literals? Bool lit. Okay, so just integer lit. We only have integer literals. Okay, and we can just swap them. So it can only be on addition, multiplication, and subtraction as something separate. So we'll do a switch case. We do switch on expr dot d infix expr dot d infix dot kind, and then we'll do a case statement of talk add talk mao. Okay, so these two, they share the same commutative property. Case talk sub can come something else. Okay, and then default break, do nothing. So swap LHS and RHS. That's easy. Yeah, that's easy. Okay, and top talk sub transform to I don't want to sub these. I just want to perform negating. So we need to create a new node. No, transform to negative const plus t. So we perform a HIR expr, which is neg. No, it's gonna be like this. No. Expr prefix And then the d prefix, is it prefix? Yeah, d prefix up equals expr. Here, there's a specific thing. Prefix expr k sub. Okay, and then the prefix is expr to RHS. That seems right. And then we'll convert the. We'll have to swap the LHS and the RHS. So what we'll have to do is convert the RHS to this. So we'll go on RHS. And then we can do, yeah, we'll make the new RHS this. Yeah, dump. Simple. What's the error? From int. Oh, it's here dump. Okay, and then we just swap. Just copy the whole thing. What we can do is do some case fall through. Yeah. Okay, easy and default break. So, let's just go test this. We can go test this right now. Nothing happens, but we can just start. So, add vi32 equals v plus 50. What happens now? Okay, constants, which way do the constants go? Terms, so terms should have been swapped. Why did that not throw? If rhs.kind equals expr integer literal, switch expr d infix.kind. We're not actually swapping them. Okay. All right. Great. That do it? Yes. So we're moving constants to the left. Move constants to the left. Yeah, we can do 50. All right, now it's 50 plus actually, okay. We need to make it end up like this. Right now it's like this. We need to make this end up like this. And that's the further rule. So this is the first rule. We've applied the first rule. Let's apply the second rule. Well, I don't know if it's second rule, but it's one of the rules. So we'll see what we have next. So this is rule 1, 2, and 3. Okay, let's do some more complex rules. So T1, T2, T3, and let's just flip them around. Now, we can only perform these things if they don't like change the flow of things. So let's say we have to keep effects in mind. So let me explain a bug that could probably happen. Let's keep effects in mind and try and apply rule 4. So let's grab rule 4, bring it over here. So let's do something like, which way is T3 going? Let me find out if this puts in and makes things worse. Because you're evaluating 2. I don't know if this causes errors yet. We'll find out. I think this may cause like changing of this might change the semantics We'll cross that road when we get there. Okay, well, let's just do rule 4. Essentially, it's matching on that and then just swapping them. So let's do rule 4. Let's do rule 4. Rule... We'll do the rules later. So what is rule 4? Let's bring this down so you can see it better. So, essentially we're going to have to check if... and we can combine rule 4 with rule 5, right? Yeah, let's combine rule 4 and rule 5 together. If expr Okay. Expr.kind. If okay, no. If expr.dinfix dot kind equals talk add or expr.dinfix dot talk mao. Bring this in here. Talk mao and bring the next one in. Actually, they both have to equal the exact same thing. So we have two cases. We'll have to go expr dinfix dot we'll have to go RHS dot kind equals expr infix Okay, this is, I hate merging Boolean shit. Okay, just if RHS.kind equals expr infix and or kind equals talk add and expr dot go RHS dot and equals expr. So the RHS is already expr infix, so RHS dot dinfix dot kind equals talk add. Okay, so this is the first one. RHS dot kind equals expr infix. So we'll just expr.dinfix kind, so talk add and RHS is talk add. Okay, so we'll have to duplicate this again. We'll put this in braces, or and we'll go talk mao. That is a long fucking line of code. Like, I don't care. So all we have to do is what did that do? Did that work? Wow. Okay. Thanks, Copilot. Let's actually just verify this. T1, T2, T3. LHS is a new expr infix. T1, T2, and T3. Huh. Alright, well, let's see. Let's see, did it work? Let's go clear. Well, by the looks of it, it did. It moved the 50. So let's go through all the rules one by one. All the rules one by one. So it's 50 plus V plus 50. So what it did is it moved 50 over here to this, and then I think rule 4 kicked in, or whatever rule it was, and it moved this to this. Done. So this to this to this. Simple. It's pretty simple. So let's do some more. We'll check this for multiplication as well, and make sure that doesn't cause any errors. Yep. So that multiplication stays, but if there's multiple multiplications, it moves them. DWRR. This is like canonicalization of expressions. Kind of like the same thing, but we're not using this for optimizations. This is just for catching overflow errors early. So essentially what I'm doing right now is a normalization pass. So the reason why I'm implementing this normalization pass is, so last stream I was implementing a lowering a tree IR. I was lowering a tree IR into something like a SSA based, not SSA based, but a statement based LIR like thing. Master Snoods is rating with parties. Wow, thanks. 17. 17 people. That's nice. Arch, yeah, that's me. I use Arch. Okay. For the people who are showing up, I was just explaining what I was doing. So, last stream, I was implementing a. So right now in my compiler goes from source to HIR right now. HIR is essentially, think of it as the AST. So last stream I implemented something from going from HIR to LIR. So this is lowered IR. It's more like it's a more lowered representation where control flow and assignments, they're all statements and things like that. And LIR is just really close to HIR, but it just with some minor things changed. Like I went over it at like the start of the stream. Oh yeah, it's sorry. The OBS is, yeah, so I went over at the start of the stream. So basically, why don't we just cut out the middleman and just go to lowering, not lowering, but like HIR normalized. Master Snoods. How's it going? Doing well. Just working on the compiler. Yeah, so essentially we're going from the HIR and we're normalizing it. And essentially what normalizing does is all control flow expressions that return bang, so no return, would be lowered to explicit statements. Function value expression is now a ret. All the code's been DCE'd. Proper reassociation. All assignments are statements. Essentially, we're turning a functional expression-based language into one that is statementized or imperative language like. So I went over some stuff at the start, like fc bool equals fc 250 else 12, and after a normalization pass or some kind of like this pass that we're going, it turns it into this. So do to open up a list of statements, and then if c, there's a intermediate variable here, and then return that. And this is how like normalization pass works. And even something like this, if v equals 50, because assignments are expressions, I'm copying C assignment semantics. So yeah, if v is greater than 50, v equals 50, greater than 50, v else 50, and lowering it is essentially you hit here, and this gets hoisted out into a statement, and then it just does the same stuff as before. Now, the reason why I need this is because you can use control flow. This is like a zig and stuff like that. Things like break, continue, and return their expressions, and they return the no return. They return no return, or bang in Rust, or bottom type in like Haskell. So I mean, how do you lower something like this? Essentially, the ret, this is a constant expression, and this is a ret, so it should just be lowered to that. Yeah. I'm copying I'm gonna have what's it called? No gotos in the language, but I'm just gonna take Zig's block jumping, block labels, and things like that. If you have that, your language is basically you have all the stuff of goto without actually needing goto. DWR. Does HIR have if while for constructs? Lower to ASM just immediately. Okay, so the compiler went through multiple like life cycles, right? So at the very basically like a week ago, the compiler compiled immediately down to control flow blocks, a control flow graph with blocks jumping all over the place, and there was no if while for constructs and things like that. Yeah, so do I want to lower that to AS and branch? No, not immediately, not immediately. So this HIR is just an AST, but I'm turning all of the control flow stuff to not produce a value. I want it to write to intermediate values, things like that. It makes analysis easier. Spike spares. In Rust, or no-op expressions are the unit type empty tuple. As rarely used internally on Nally. Do I need correction? Yeah, so the empty tuple, the unit the empty tuple is a unit type. It's basically the void. It's basically a void in C, but you can use it as an expression. What the exclamation mark is no return. It's not a stabilized feature of Rust. I don't know what Rust, what the status is now. What I remember is you can do something like this. You can do like test, do that, loop this. And this is an infinite loop, so your function tests to no return infinite loop, and this never returns. This is the only places where I've ever seen the thing used like that. In this language, which is this, how loop works is just loop expr. So you'd need to put like a do block to do useful stuff in here. So you can just do loop empty tuple, which is just infinite loop, do nothing. The return value is always that. But I want to since ret is going to be an expression, I want to find a way to force this down to statements. So this normalization pass, it's one of the easiest things I've ever written. It's not very hard. All it is I'm running over all the expressions and I'm returning a st none or st poison. Essentially, what it means is, I think I explained at the start. How would you? I'll explain how would you lower something like this, or normalize something like this. So the LHS is 20, the RHS is ret 50. So when you lower them, when you perform lowering, so you perform lowering on the left hand side and the right hand side. Spike says, and return 1 evaluates to empty tuple. No, it evaluates to no return. Because imagine if you had something like this. No, do, ret, something, and then more code here. More code here is essentially it's not reachable at all. You could assign the value of ret to A, and that would be typed as no return. And this is perfectly fine in the eyes of a functional type system, because you can't read the value of A, right? I mean, you could possibly use A in more expressions, like, because the bottom type is basically the bottom of all types, or essentially the parent of all types. So this coerces into anything. So you can do this. I mean, this is perfectly fine in the eyes of the functional type system. Because ret, you don't even get to here. You'll be out of the function by then. Yeah, that's right. So the no return, or the bottom type, there's two things that are pretty important to understand. Okay, so there's a reason why this is called the bottom type, is because you cannot construct a value of the bottom type. You'll never. It looks nicely typed here in the eyes of the checker. This is fine. But you'll never actually be able to read a value of A or something. There is no value here. It's like it's just not possible to construct a value of it. But what this is the unit type. The unit type only has one value, which means there's only one value to construct. There's no need to store it or anything. So this is good for the return value of a function, things like that. So think of this as the void, as void in C. Except for now, you can use that in an expression. Yeah. So we'll start by lowering. We'll start by normalizing this. So you go LHS equals 20, RHS equals ret 50. So to inside here, just ignore all of this reassociation stuff, but here, transform LHS and RHS. So we're calling LHS and RHS, and we're calling this, we have this thing, this wrapper, it's called a poison. I'll explain that in a little bit. So, essentially, we'll normalize the left-hand side. And what does that return? It returns nothing, it's a no-up. ST none. And there's nothing to change about that left-hand side expression. And then we'll go to RHS. What does that return? It's a poison. Why is it a poison? Because this, the RHS returns a value of no return. This is a global effect, and reading the value of it, you'll get nothing out of it. So essentially, how it works is we'll start by doing the LHS. Okay, so we know the LHS is 20, and this is our list of statements here. We'll start parsing the RHS, and the RHS returns poison, returns nothing, but we'll append a statement here to 50. So this is appended here, and this poison will bubble all the way down. So how this works is define poison expr. If expr equals st poison, return st poison. So let's say the right hand side is a poison. This will bubble all the way down to the return here. Construct return value. If NHIR expr does not equal st poison, construct a return with the value of here. Else ignore it. So lowering something like this just turns into ret 50, because without it, here like this, it's going to insert a ret anyway. But if it gets a, yeah, it's essentially equivalent to that. If it gets an st poison coming down, it won't generate the extra ret expression. So you can just do this, ret, and this is all perfectly fine in the eyes of the checker and everything. And this just goes down to a ret 50. It's super simple. It's like short circuiting with the left hand sides and the right hand sides. With this normalization. Yeah, so you can even see in expr return, we perform a poison on the expr, and then we just re-push it to a list of statements. So we're essentially unwrapping, we're essentially decomposing all these nested expressions that produce like control flow effects and things like that, and we're moving them down into a list of statements. So when you call NHR expr, you pass in the description of the IR, and then you pass in the HIR expr t, which is a list of statements, and the current expression. And what you do in a function is, first you construct a list of statements, and you just construct them here. So we're essentially flattening everything. Everything's flattened, which is great. And I'll show you an example. This thing. This is like an if statement. And I explained down here where you have if c bool do. You're flattening them into if c, else this to this, and then ret that. Yeah, so this goes this is a do block, and these are on the same line. These are obviously, this is the weird printing, so it's just if c do _1 _1 assign, and then ret _1. Yeah, and the if statement constructs a new if statement, and then what it returns is it just mutates the existing expression and turns it into a local, expr local. Spike spaz. Let's see. Okay, so let me bring this on the front, on the big screen. Oh, whoops. Yeah, the okay. These aren't essentially equivalent. What this return doesn't construct an empty tuple. It returns no return that coerces to empty tuple. It coerces here. So I don't know if there's a way to inspect the type of something. But if you remove the type annotation and probably put it in mir, MIR. First doesn't, well, it's, well, not, it automatically, like implicit conversion. So the bottom type is the parent of all types. It'll implicitly convert to this thing, in the eyes of the functional type system. Keep in mind, this is different to integer coercing. This is the no return type, so it probably has specific exceptions. What does the MIR give us? Why is there so much MIR? Oh, it's eek. Okay, well. Yeah, it just removes all the nodes and stuff. Anyway, I don't know much about the internals of the Rust compiler. I wish I did though, because it's pretty interesting. Okay, well, where were we really? We were essentially before the raid. We were implementing. I was implementing, just reassociation. So the reason why I want reassociation is just because of this. Let's say you have 50. Oh no, it's all good. I like the tangents. Let's say you have something like this: 255 plus a plus 1. All right, and we'll just assume that all of these are U8s. So k, so U8 plus U8 plus U8. These are all U8s. And you can tell, I mean, this causes a this is an overflow error. This is gonna cause an overflow error at runtime. And I'm pretty sure this returns overflow errors. I'm pretty sure Rust performs some kind of a reassociation and throws an error. I tried to check it at the start of the stream, but I seriously I couldn't find it. I wish I like saved the code that I wrote, because I remember raising an error like that. Anyway, what I'm trying to explain is, imagine if the compiler could take this 255 plus a plus 1, reassociate it to 255 plus 1 plus a, right? Then checking for overflow, trivial overflow is so simple. You can just perform const prop and get 256, and oh wait, that's outside the range of a UA. So that's what I want to perform. This I think it's like yeah, normalize it. You can think of it as like canonicalization, normalization, but this is just what I want to perform anyway, because I'm going to perform further checks later on. So what we've done so far is, and this is just some notes here. Yeah, this don't perform reassociation but not const prop eval. That's left for further passes where compile errors are raised. This is just to catch. This is just to arrange expressions to catch overflow errors early. We'll have further reassociation passes in later IRs. Okay, so overflow errors, yeah, floating points, they don't have properties. Okay, so transform left-hand side and right-hand side, bail out if they do a poison. And here is my rules, my reassociation rules. So a term plus constant, constant plus term. So essentially, what we're trying to do is move all the constants to the left-hand side. All the constants are going to the left-hand side, and all of the terms, the ones that you don't know, are going to the right-hand side. Yeah, so t minus c just goes to negative c plus t, and yeah, so essentially we're bubbling these things down to the left, and then you can do these constants to merge these like that. So I think I have an example that uses rule 1 and rule 4. I'm pretty sure this is the one I showed at the top. I think it's like 50 plus k plus 50. And then essentially what it's supposed to do is it's supposed to do this. It's supposed to swap the order of these. You're applying rule 1, and then applying rule 4 will move it to this. Okay, and if you take a look at rule 1 and rule 4, take a look at rule 1 and rule 4. Rule 1 is this, and rule 4 is this. There's a note that I put here that says T are terms, C are constants, and constants are also terms. So if you see here, T plus C equals C plus T. So this is applied to this hand side. So you're putting the constant on this hand side and the term on this hand side, and term rule 4 is term. Oh yeah. These are being applied like this. Rule 4 is term plus term plus term equals, and then you're moving, you're merging T2 and T1 together like that. So we're essentially we're applying these like shifting rules to force everything to the left hand side. You say, what's the difference between rule 1 and rule 2? This is just plus, and this is multiply. They're the same rules. I do rule 1, rule 2, and rule 3 all in one go. Do them all in one go. Yeah, so add and mul is just flip. You just flip them. So it's super simple, and only if the right hand side is an interliteral. Yeah, we're just flipping them. Super simple. The only difference is that this one's addition, this one's multiplication, and for like subtraction, all we can do is just yeah. So right now we convert this to a negative c, and then we just do a fall through and then flip them anyway. So I implement them. I implement rule 1, 2, and 3 all together. Super simple. Now what I did next is rule 4 and 5, and you can see that here. You know, create a function. We'll go function f equals 50 plus k plus 50, and then we'll go to GCC and we'll run it. K is 32, and we'll see what happens. Yeah, so plus, I used like some Lisp notation, but it's reality is the same thing. 50 to k. I think I want to change the way I print these. Yeah, I prefer the other way. I put these in printfs. Yeah, much better. Okay, so we have 50 plus 50 to k. Simple. Okay, well, let's do more rules. I kind of want to get C code generation by the end of the stream. I feel like it'd be really easy, because I've worked on V, and V did C code generation. Alright, let's do the rest of the rules. So 6 and 7. I feel like they could be implemented in terms of each other, basically. Okay. Yeah, let's do this one. Remove that to do. So we'll need to check if RHS.kindness infix. Are you also planning to evaluate fully constfold expressions in AST later on? So I plan to do full definite assignment analysis, conditional constant propagation, and language-specific optimizations, all in the HIR on a tree-based representation, like a lowered tree-based representation. I'm not going to do it in control flow graphs and things like that. So essentially, I'm going to do the constant folding on a tree. It's going to be on a tree, and then further, yeah. So it'll be folded in a tree, and then I'll just dump everything into a either C or another IR. So a control flow graph SSA IR. Yeah, you say damn, but it took me a long time to it took me a long time to come to the revelation that, like, yeah. So sparse conditional constant propagation, or essentially just constant propagation with presence of control flow, that's super easy to implement. And it's super easy to implement on the guise that it's gonna work in the way the user looks at it, like syntactically, right? If you write, the reason why I'm not going to unwrap everything to SSA, the reason why I want to keep everything into trees, is because the user's gonna see the syntax, and if something doesn't propagate well, the user will be able to see that inside the syntax. Anyway, it's a bad explanation, but essentially, this normalization pass, after normalization, it'll put everything in nice statements, and then I can perform all of these, specific analysis. So I'll go over to what I want to do in the LIR. So this is the document I wrote yesterday. just replace the word LIR for HIR, or normalized HIR. So the normalized HIR is for proving pattern exhaustiveness through data flow analysis, proving definite assignment through data flow analysis, proving invariance through data flow analysis, performing language-specific optimizations, performing certain global optimizations in inlining, and running code at compile time. I ran through the entire explanation last stream. I'm gonna have a VOD out pretty soon. Like, I have a YouTube channel and Discord if you want to join and just, like, catch up when I'm streaming and things like that, and when I upload. But I explained all of these last stream. So essentially, this is what the normalized HIR is supposed to do. The normalized AST. This is all possible with the tree representation. So if I do normalization, this can easily be done, and then I can just go straight into SSA and things like that. Okay. Does that work? I don't want to fill that in and have it be wrong. Oh, wait, fuck. What did it do? Okay, well, let me just check. Is this even right? Okay, so okay, LHS kind is infix, and dinfix is add. Add, and RHS kind is literal. Then it has to be constant as well. Okay, this I hate. I wish there was like pattern matching. I wish I had pattern matching in C. But like I'd be able to do this with pattern matching. So we'll start LHS kind equals expr infix. No, I'm not following your stupid thing. Okay, infix. Is that right? LHS. So it has to be either this thing or this thing. Like add and. Why C? Because I like it. I like writing in C. So I use C. I could say things like portability and things like that. In reality, I'd be doing this a lot quicker if I wasn't in C, but where's the fun in that, right? Okay, so of course talk add. So we need to do two things. Okay, good. All right, don't worry. Yeah. Essentially, like, I don't know. C. There's no fun if you're not writing it in C, right? I like writing in C. But when I get this compiler bootstrapped and everything, I'm gonna be writing. I'm gonna like immediately get out of C as quickly as possible. I'm gonna just rewrite the compiler in its own language as quickly as possible. So these things take too long in my head. So LHS is infix. So the RHS has to be integer literal, and the LHS dots the infix dot LHS is an integer literal. And I can just duplicate this for mal. Yeah, I can duplicate this. You know, I could just extract the common sub expression like that, and then do that. Oh, Jesus Christ. Why is it? Alright, fine. Good enough. Okay, we'll put this on the same line, make it so long. Alright. Let me check if I did it right. So C1. So LHS is integer literal. C2 is the RHS. Okay, so C1, C2, and T the term, and then transform to C1 plus T. Easy, easy. I think that's the last. That's the last rules. Okay, so I'll go. This is. Yeah, it's easy if I just duplicate the rules. Actually, I'll just go rule 1, 3, rule 4, 5, and 6, 7. Great. Now, let's see if these rules apply properly. So C1. Yeah, let's go C1. Doesn't that already work? Actually, you know what? I'm pretty sure rule 6 and 7 are fucking duplicates. Okay, I copied these rules from Stack Overflow. Okay, just delete this whole thing. All right, these rules are duplicates. I just remembered that. Okay, good. Okay, I'm pretty sure those rules were for constant propagation, for constant evaluation. But I'm not doing that, so I don't even need those rules. Okay, good. Anyway, we did it. We did the normalizer. So let's just let's bring out the factorial function, and let's just do some C generation. Let's just write up a super stupid quick C code generator. All right, ret main factac. Okay. Well, let's do cgen. Let's see. Oh shit. All right. Well, okay. I'll make a commit now. I'll name it. What am I gonna name it? Let's call it. I'll do norm. It's a stream 16. Yeah. So there's supposed to be 15 in there, but I know it's stream 16. This is a norm. Normalize and reassociate. Okay. Good. So commit. And then now let's do C code generation, just because we can. Just because it'd be nice to have this by the end of the stream. C code gen's easy. You just walk the expression tree. So so let's go to pass.c. So first we perform topological sorting of all the symbols, and we just check the sanity, and then we check them all and normalize all, and then we want to do code generation in the order of those symbols. We probably want to do DCE as well, but I'm just gonna do cgen for the time being. Okay, just debug. I just want to debug print cgen. So I'm gonna copy. Yeah, pass normalize all. I'm just gonna include. Yep, all.h. We'll name this pass debug cgen. All right, now let's generate C code. Yeah, this is pretty similar to what the V compiler does. It just runs over all the symbols and just runs over all the expressions and just generates them. So, yeah, we'll do a just copy this, paste it. So globals, no, set not reached. And proc, we'll just do GC proc. No, what's the thing? We'll just take this. Okay, and I'll do a file pointer, so it's easy. All right, so we'll just put std out as well. All right. So GC proc is simple. What we should do first is run over all the symbols and generate their signatures. So we'll do that real quick. We'll I'll just duplicate the top. We'll generate signatures. Symbol. Proc. Okay, thanks, C++. We'll call that G. How was it called? G. Okay, well, all we have to do is just match R types to C types. So the only types we're going to support right now are integers and bools. There is this is just a good proof of concept. This is just a good proof of concept because later on I'm gonna have to take a lot of time off to implement lowering, and there's lambdas in the language and closures and things like that. So they'll all need their own passes, and but this is just a test for now. So we'll have to go to all.h and construct some associative array. So these are all the types. There's tuple, function, closure, closure union, type, pointer, slice, array, and symbol. I have to find a way to G type. Generate a type. I mean, how it works is just t info t type info equals type get. G type. Well, we have proc dot ret type. So we have ret type printf. It's proc.name. We need the symbol as well. Oh, wait. All right. Oh yeah, we'll need to find a way to do name mangling as well. So let's say you have function main, its actual name is main.main because I'm copying V's and goes module system. So everything's delimited with dots. So I need to find a way to just convert them into mangled names. So gmangle with a istot, which is an intern string. So we'll just get a const sv from and do a sterline. Yeah. What's that? Is this in use size? Yep. So it's a. I don't think. I think I just have size t. And just 4. Alright, great. Let's change attention tabs. Let's do $sign. Okay, it's gmangle. Gmangle. Just do gmangle. Let's just go for arguments. No. It's supposed to be like that. Okay. Good, and then we have gprintf. This new line. Okay, well, let's just run over the whole thing and see what happens. What does it do? Did it return it? Cgen main factdac. Did it printf though? I'm surprised. Why is it not working? Alright, fine. Back to printf debugging. Yeah, we'll just printf. Wow, it never even gets to here. Okay, how does that happen? Oh, sim.key. Okay, sim.key. Okay, alright, that's my fault. Okay, let's see it. So, main.factdac. Wow, it does nothing. Why does that work? I haven't implemented gtype, so let's just printf gprint IR32 for the time being. Let's just do that. So IR32 main factdac IR32n, so I have to do a space after that. Ac, and then we need to put a yeah, okay. Let's we'll make the to the standard error. Standard error. Then we'll pipe. We'll go pipe. How do you pipe and ignore standard out? Okay, let's go dev null. Okay, and then we'll go at need to pipe 2 to 1. Well, let me just look up how to pipe std error to std out. Okay, it's this way. Wait, right? It's 2, 2, 1. Okay, great. And then we'll do bat LC. No, LC. Okay, good. And then we'll make the parsing file thing. We'll make this just printer. Easy. Now, here's our long script. This stupidly long one-liner that clears it and prints what we have so far. So main factdeck, main factdeck. Okay. Now let's do the rest. So all we have to do now is iterate over the whole thing. So let's so right now we have to assert that proc the proc desk to the top level. Was it proc? Here's HIR blocks. Oh, top level, body. All right, and then we just need to assert body.kind equals expr do block, because that's the only thing. And then we need to just run through all the statements. No. Okay, so looks like this HIR expr t body d do block dot exprs. Okay. Great. Let's turn that into a pointer. All right, now we have to do we have to match on statements. So all the statements currently are as like this. So I have to do, let's see, expr kind. Let's find out all the statements that we have right now that we're lowering. It's not lower, it's normalize. So what we'll need really is, let me just take all of these and then just delete the code. It's so dumb, but this is just the way I like to do it. Yep, expr if, so if is one of them. Assigns one of them, returns one of them. Okay, good. So these are all the quote unquote statements, but they're actually just expressions. So we just go one by one. Convert these to C. So let me do reprintf. See, this is one of the best things about it's one of the best things about having a like a normalization pass, because you have this functional like list of expressions that can all be nested, and those nested expressions can perform effects and things like that, and you need to lower them down so you can put them in an imperative form for 1, analysis, and 2, code generation. In further iterations of this compiler, it's not going to generate C, right? C is going to be a secondary thing only for portability reasons. I want to go to a different architecture, and I don't have it. I want to get my compiler on someone's computer. They have a C compiler. That's how they bootstrap. They're going to bootstrap C using C. But later on, I'm going to implement like my own compiler backend. It's going to generate WebAssembly, RISC-V, and x86. And that's where most of the optimization is going to get done. But for now, generating C is the easiest thing in the world. So I can just generate C now. The sooner I generate C, the sooner I can bootstrap my compiler and things like that. But C is not going to stick around. C is not going to stick around now. Now, what the V compiler does, because I can talk about the V compiler if I'm on the team, like I've worked on it, and I can say that what they do is pretty futile, because they take their expression-based syntax and everything and all the C stuff and all the V stuff, this expression-based tree list of expressions, and they just have a big tree, the big AST, and they do nothing with it. And they try really hard to generate C code in one go, and they have to do all this backtracking, inserting intermediate values and things like that. What they would really benefit from is a normalization pass, like I'm implementing right now. All right. If they had this normalization pass, language would just be so much better. This would make things so much easier. So, terms. So, like a really rookie mistake to me. Well, the whole V compiler is. It is. I mean, it's just the hard truth. The V compiler is a mess. It's an absolute mess. They've been working on it for like 6 years, and it hasn't really gotten any better. So, hey, I was planning on working on it on the V compiler and really just trying to save it. I was planning on saving it. Like I had like a whole design document of exactly what I wanted to do. All of the stuff that I'm implementing here, I probably would have implemented in V if things really went that way, but they didn't go that way. Uh, I don't know. If you look in the V compiler, it's horrifying. It's now the reason why I think it's horrifying, and I think I have actual experience to back that up, is because I implemented the WebAssembly backend. I did WebAssembly code generation for V, and imagine trying to do WebAssembly code generation on an AST. That's very hard. I worked with what I had, and I implemented something pretty good. Actually, I'm pretty proud of it. I'm pretty proud of it, but I feel like they I wish they just implemented some kind of normalization pass that made V simpler. Right now, it's a mess with multiple backends implementing the same thing. So there's code duplication. Uh, it's like yeah, it's just silly. Well, I don't have assignment expressions as well. I can do that later. Okay, so let's just switch over what we have so far. So symbols. Okay, so let's just switch over what we have. So keep in mind, this is just a proof of concept. I just want to get done just for the sake of the stream. Yeah, I mean, I don't even do bounds checks at all. I mean, I should be doing them. An expr literal shouldn't be a string. That sort of thing. All right, expr literal. Let's do expr local. Well, it's not name because locals need to be prefixed with something. I'm gonna prefix it with triangle local, and we're gonna pass a IR desk t desk and a R local t local. And just a g printf. Yeah, u is local. So I'm gonna prefix things like that. Good. Okay, let's do expr infix. I wrote a blog post about implementing something pretty similar to this. I implemented a V code generator that did basic C code generation, just to explain to new contributors how to actually work with a compiler. It was a while ago though. Let me force quote these as well. Alright, how do I debug print this in the table? Yeah, do this. Tuck up stir. Alright, simple. Alright, so these are all the expressions. There's really no expressions here. An expr calls one. Alright, so you want a gmangle call. Okay, so gmangle local. Yeah, we'll do case symbol as well. Symbols dsym. Okay. Cool. Okay, good. Sure. Let's do assignments. We'll have to do GHIR expr on the left hand side. And the right hand side. Okay, and then if is super simple, it's just generate the cond. Oh, gproc. Oh yeah, we'll need to add tabs like a tabulation. Equals 0. Yeah, we'll do G. That's almost done. All right. The desk is important as well. All right, then default we just call f desk and expr. Okay. All right, and then what G statements does, it needs to print the amount of tabs. So for print T. Need to print tabs as well. All right. Good. So we call gstimate for the starts. We need to call gtabs. Group F, and then we call need to this, and then increment g tabs plus plus. Yeah. Then. Okay. Let's duplicate it for here. All right. Sounds good to me. So what about g? G statement and G statement. Good. Good. Simple. Let's run it. Okay, let's just delete all of this. All right, let's do it. Null sigabort. Where? Oh shit. Assertion stir does not equal stir none failed. Okay. That's just something simple I could do. Okay. Yeah, because locals can have empty names. So, name is also okay. If name is not equal, I stir none. Else. It's just this. Okay, does it work? Reachable fail where? So which one are we checking? Okay. So it's got to be multiplication, right? Yeah, let's do print kind. Just run it out. So where's the failure? And delete that too. So it's in here, and what's the kind 13? Ah, prefix. Prefix. Alright, that's simple. I think I have that here, prefix. No? Alright, so alright, that should be it. Is that right? If I don't know if that's supposed to be right. It's supposed to be a new line at the very end. Yeah, this doesn't look right. G printf new line 2. Wonder why that's happening. Oh yeah, okay. The assignment needs new lines too. We just need new lines. Alright, so if n is less than 1, 2 equals ac, you're calling main.factac with -1 minus n0. I think it's supposed to flip -1 to positive. So that's okay. This is where this is where like dumping and generating code can help you in compiler stuff, because generating C is just such a much better representation than just printing the ASD. Okay, so we can start by actually generating the procs, right? The stubs. Start the def. Space, and then a gmangle local. Okay. That's better, so we're mangling. Radio generation is proven correct. Yeah. Yeah. It's one of the simplest code generation things ever. It'd be much harder to prove something like x86 code generation correct. It'd be much harder. Much harder. But this is just simple translation of expressions. Okay, so let's gproc def. New line. This needs a symbol, so what are you calling gproc? With the symbol, and then we'll call gproc def with yeah, and then we'll increment tabs. Sure, what does it do now? Return 2 isn't on the right line of tabs. That's weird. Alright, great. Now let's get this like negative stuff working. I think I can just disable the reassociator. Just for like, I don't really want to negate my literals. I feel like that will cause errors down the track anyway. Okay. I mean, we can try it. Let's go into godbolt and try it. Or we can just pipe it to a C file. To a.c. Let's see, a.c. Is it generated? Okay, well, okay, fine. I'll just copy this. Yeah, I'll just pipe everything to, let's see. What? Okay. My fucking build script is just taking the .c. Okay, I'll delete this. Yeah, the output is going into STDR. This is the worst setup in the world. Just ignore it for a sec. Alright, good, fine, done. I'm taking this. I'm going to godbolt, because I'm not bothered. Yeah, I'll go to godbolt. Oh, I32 needs to be type deft as well. Okay, just... Is that right? Is it this way around? Is this way around? Right? No, it's this way around. So underscore 2. We need to... we need to define all the variables at the top. Okay. We need to define all the variables. Okay. Let's do that. Yeah, so for U32, I equals proc arguments. Yep. Okay, sure. Tabs. Alright, this is the most botched C code generation thing, but you'll be surprised how often they do it this way in multiple programming languages. Alright, good. Now, this is supposed to do tail call stuff, right? I think I should just make these static too. Fact act with the accumulator is supposed to be static. Okay, so this did tail call optimization, so let's just go int min and call it with we'll fact act this with 20. Oh wait, no, that's gonna be a insurmountably fucking huge number. We'll just call it with 5. And then we'll printf not std, scd, what was it called? scdir. Alright, let's see it go. 120. That wasn't so bad, was it? I think that's fine. I think that's where I want to end the stream. Yeah, I think that's where I want to end the stream. Okay, so before I end the stream though, I think I want to make, I don't know, like a tests folder, and then just put a bunch of like language code in it and watch it generate C. But I'll leave that until after the stream. But right now what I have is great, so let's just commit that. Yeah, it's just called cgen, but I know this is just for debugging only. Okay, so stream 16. Basic. What did I change in here? Interesting branding. I've not seen this fork of vscode. Oh, really? This is called vscodium. It's a not stripped down, but it's basically a fork of VS Code that removes all of the Microsoft telemetry, all the Microsoft branding, everything. So I'm safe to use this, and no telemetry gets sent to Microsoft or anything like that. Yeah, they just took VS Code and added their own stuff onto it. The VS Code is MIT, so yeah, they can do this. So, let's probably pass. Let's see, and 16, so let's sync them. Yeah, so I'm using Copilot because I'm an open source developer in some open source organization, the V organization, so they just give it to me, GitHub. It's really nice of them. Oh, since last? Really? Yeah, they've always had this weird seaweed logo. But other than that, I mean, if you guys want to see, this is a raid, so this is a lot of new people that haven't really seen my stuff. You can go to my Twitch profile and click on my YouTube. I'm gonna upload this VOD later on. I have last stream's VOD that I need to upload. And I usually ping people in the Discord if they want to about new uploads and new streams. So if you're interested in that, this is currently the 16th stream of me implementing my programming language using all the skills and experience that I have really on working on other compilers and things like that. Yeah, you know, I seriously I have faith in this language. It's really like nothing I've ever thought of. I mean, because the new languages that they come out these days, they all do the same stuff. It's all imperative and things like that. And um, I want this language to replace C for me, right? So I write a lot of things in C. I write literally everything I can in C, right? And there's reasons why I like C. It's just because of its manual nature. Everything is manual. But there's some things that I would really like in C. Things like not proper macros, but maybe lambdas, like inline lambdas. Closures would be very nice. Closures would be great. They fix issues with like a Q sort and passing in void pointers and things like that. And just embracing some sort of like functional style, just changing the syntax and things like that. Um, yeah, like this will replace my C, and I feel like no other language is doing what I'm eventually going to be doing, especially with these things with analysis, and because I'm going to do definite assignment analysis. If you ever heard of Cyclone, Cyclone is a C dialect that is essentially memory safe C, and Rust used a lot of Cyclone's ideas and things like that. See, what I really want is this middle ground between Rust and Cyclone. I want to use, I essentially want to implement the things that Cyclone has done. So I want to implement definite assignment analysis. I want to make sure all my assignments to values are initialized and things like that. Because I use a lot of uninitialized values in C all the time, right? I have an uninitialized value, I have a condition that initializes it, and every time I use the variable, I check the variable like inside that condition. There's a lot of places where I use uninitialized values in C, and I want to make that safe. I want to make that safe. So yeah, and even Rust does not perform these special, like even highly advanced assignment, like specific like definite assignment analysis. Stabilize one cell. Oh, I think you mean like you have a variable and then you assign it, and then yeah, I've seen one cell in the wild. I'm not really much of a Rust programmer, but I kind of know what it is. Um, See, the thing is, here, let me create an example. Something like let a if c a equals something, if c use a. This is something that I want to support in the language from the get-go. Why don't just initialize everything when you declare it? Because that's not fast. It's not fast, and it's not it's uninitialized values also signals to the user that the value is initialized, uninitialized. It's like a guard. It's like a guard. Yeah. One cell. I can take a look at it. I think I know what you mean. I think it's just called let a once cell. Yeah, this is kind of similar to some functional stuff. Anyway, so if c a dot set something, and then if a has use a, right? This is, I'm pretty sure, I'm being optimistic here, but I'm very sure that this code will be optimized to that. Yeah. Cell get or init hello world to string. I've seen this code in a while before. Yeah. See, the thing is, I'm very optimistic, and I'm very sure that this code will be optimized to this code. I'm pretty sure it'll be optimized with the same semantics and things like that. But it's not I don't know. It's not. I don't really like going through these other indirections, and especially it introduces complexity in the code that you're writing, and the amount of compiler complexity you need to have that function work. People say like in Rust. if you're implementing a Rust compiler, I think they talked about this in the GCC RS thing. They said in one of their blog posts, Rust is a language where if you don't have everything working, nothing works, right? So it just represents this kind of like this hyper complexity in, because I mean I don't know, I just don't want to. This doesn't seem very like workable for me. I'd much prefer it to be something like this. I'd much prefer it to be like the C code that I write. So I'm pretty sure they compile to the same stuff. Probably the Boolean expression gets merged together. But I want this to be possible and verifiable in the language, and that it's not hard. It's pretty simple to get this kind of thing done. Um, yeah, I'm gonna get back on track. Essentially, this language is gonna replace my C, right? You know how it'll be like a mix of Go. You know Go compiles really fast and it performs optimizations without the need for LLVM and things like that. I just want fast compilation and essentially my own C, like, and it's a functional language. You know, um, I'm gonna put a lot of work into this. I've already done basically a lot of research over the years. Like I have like, you see here, if you just look here, you go to like new lang 1. This is just all of this stuff, right? And then you go to new lang 2. And then I have here all of this stuff, and then late docs. I have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 documents on LIR, where I just talk about optimizations and all of these things. Yeah, it's just a lot of stuff. I believe in this language. I feel like I have the skills to get it done. I disagree on the foundation that if my Rust code compiles, it probably works. If one part is broken, I have to fix it and write tests. Higher quality crystallized design. I think what I said, that like if everything has to work, yeah, if everything doesn't work, nothing works. That was in relation to the complexity of the Rust compiler itself. Um, that was like, you need every single language feature to be implemented to get a basic get a basic program running in Rust. It wasn't about like writing code. It was more about the internals of the Rust compiler, because I like simple compilers. And this compiler right now, it's one of the simplest it can get, and it's one of the fastest ones, the most versatile ones they've ever worked on, really. Yeah, I don't know. I think that's where I'm going to wrap it up, though. Thanks for the raid. I don't know if the person who raided me is here, but I'll have to check out his channel. Just thanks, guys, for showing up. Yeah, yeah, like Zig. Well, the thing is with Zig, though, it has a super complex comp time system. I mean, you may think it's a simple language, but in reality, the implementation is thousands of lines long. Just you wish it were functional. I don't know. There's things about Zig that I like and I don't like. There's I think, yeah, just I want like closures and things like that, proper generics. Um, there's things that I can't just use Zig instead for. Yeah, all right. I think that's where I ended. That's where I ended. Thanks guys for showing up. You know, I'm gonna upload this to the VODs. If you want, you can join my Discord if you want. Just get further things. But other than that, I'll let you go. All right, bye guys.